Hi everyone, we're the WinLab Smart Intersection intern team.
I'm Nicholas.
I'm Kevin.
And I'm Brian.
Our group was advised by Ivan, Zoran, and Jenny. We'll start off by introducing our project. Smart Intersection uses object detection algorithms on video taken from traffic intersections to locate and track vehicles. This process is called inference, in which vehicle movements are analyzed. The results are used to determine where vehicles are coming and going to quantify traffic flow for that period of time. Ultimately, we want our project to be able to help transportation departments manage the traffic in their cities by providing insights to how traffic patterns change over different hours and days.
To that end, we had a few goals for our internship. We wanted to be able to perform inference, which would allow us to track vehicles using machine learning on video footage. We wanted to create a distributed system where we perform inference on one machine and send the results to another machine for recombination with the original stream. And we wanted to use the results from our system to quantify traffic flow information.
To accomplish those goals, we took advantage of various existing technologies. Our project is built upon NVIDIA DeepStream, a software framework used for building real-time, intelligent video analytics pipelines. It's specifically designed to run on NVIDIA GPU hardware to take advantage of their advanced video processing capabilities. DeepStream makes it easy for us to implement a working object detection system. The detector that we use for our project is called YOLO.
YOLO is an object detection system designed to be fast enough to run in real time, on live video. We use version 3 for our project. Due to the way its underlying neural network is structured, it only needs to pass inputs through its system once, hence the name. Just for a bit of background, a neural network is used to classify certain objects based on trained data in the past. This results in very fast inference times, and also allows the algorithm to globally reason about objects and their context within the scene. This makes the algorithm more successful than others at recognizing new representations of objects it was originally trained on. As you can see in the top image, initially many possible choices for the location of desired objects are present, but this continues to be filtered down through some techniques in YOLO until a good fitting box is centered around the object.
We use other technologies such as AMQP, OpenCV, and NTP as well. We'll give a brief summary on each. First, AMQP is a messaging protocol that lets us send data from one machine to another. We use a pub/sub messaging pattern where we publish the data to a message broker that the machines can subscribe to. Next, OpenCV is a library that allows us to draw bounding boxes around the detected objects using inference. We also use it to label object types and how confident our model is of its predictions. Finally, NTP is a network protocol that lets us synchronize the system times on various machines to the time on a reference machine. We do this to make sure that the boxes we draw using OpenCV are timed correctly with the original video.
Now let's cover our implementation. This diagram is a high-level depiction of how data flows through our final system. To start off, we have footage coming in from a video source. This video gets streamed to both our inference server and our viewing client. On the inference server, video is fed into our custom DeepStream application. The output inference data is published to a message broker on the same machine. The viewing client subscribes to the data published to the broker to retrieve this output data. The client runs a multi-threaded process, more on that later, that writes the inference data to memory and combines it with the original video stream. To allow for this, the clocks of all these machines are synchronized using NTP. The major components that we developed during our internship were the DeepStream application and the multi-threaded reader-writer implementation of our viewing client. Let's talk about the DeepStream application. The data pipeline we constructed is made up of various elements. A source bin decodes all video sources and feeds them into a stream multiplexer, which adjusts the resolution of the video to match the resolution used for inference. As videos arrive at the multiplexer, system timestamps are taken for synchronization client-side. Multiplex data is fed into our primary GPU inference engine. This performs inference on the video scene using our chosen object detector YOLO v3. The engine spits out predicted object locations, their predicted types, aka their class, and how confident the model is of its predictions. Objects detected are sent to a tracker. The tracker attempts to follow detected objects as they move across the screen and assigns them unique ID numbers. This tracking data is fed into an analytics plugin, which takes tracked objects and determines what direction they're moving in and whether they have crossed certain boundaries. This is useful for us when figuring out when and where vehicles are entering and exiting the intersection. Lastly, all the data we recorded from the previous steps is packaged together into a message payload. The application takes this payload and publishes it to our message broker for transfer to any number of viewing clients.
As we mentioned before, our viewing client uses a multi-threaded implementation with 2 threads to allow us to process inference data and video in parallel. We can think of multi-threading in the form of an office environment. Our writer thread is sub to our message broker, almost like receiving an email from the manager. It takes in the message it receives, parses them for inference and analytics information, and writes this information to a queue. We can think of this as if only certain instructions need to be passed to our coworker, who will use the sifted information to perform their job. This queue is also a data structure shared between both the writer and reader threads, and is used to pass information from the former to the latter. Also, the system runs in a loop, so the worker will continue to check their email to see if the manager sends any more information, and will continue to send instructions to the coworker as they come in.
The job of the reader thread is to add the bounding box information to a frame in the video once information is received from the writer thread. The reader thread reads from the shared queue to get our inference output. Back to our office example, this is when the coworker receives the information sent over. It compares timestamps in order to make sure this output was inferred at the same time as incoming video. Once the reader thread has object information timed properly with the original video stream, it uses OpenCV to draw bounding boxes around detected objects and label them with any relevant information, such as names and confidence in predicting that object. In our example, the coworker does their instructed task and then checks their email again to see if any more information was sent over. This process continues until there is no more video remaining. Here is a sample inference run on our traffic footage combined with the bounding box information, which we'll play for you now to see. We are able to detect the vehicles moving across the intersection, which was performed using YOLO v3 and DeepStream. The values in parentheses are the predicted directions of travel for a particular object, aka north, south, etc. Next to the confidence percentage, the client will also display any boundaries that have been crossed by the object. For instance, the zoomed-in shot on the right shows a car that was detected as exiting the intersection from the south. These line crossings are counted to figure out how many vehicles passed through the intersection and where they were going.
Future improvements we're looking to make to our system include training a custom YOLO model specifically designed to detect vehicles. Our current model we use is a more general one, which is trained to detect a variety of objects. We are also looking to update our project from YOLO version 3 to version 4, as it comes with various improvements, but is not supported in DeepStream by default. Lastly, we're looking into ways to use point clouds, which is a form of depth data, to increase the accuracy of our detections.
We hope you enjoyed this high-level overview of Smart Intersection. For more information on the technical aspects of our project, feel free to visit our website to take a look at our notes on what we learned over the course of this internship. Also, we'd like to give a special thanks to our advisors for their guidance, and a big thank you to everyone for making this summer so enriching. Thank you for watching.